line integrals and possibly Green's theorem maybe on this night. And, you don't really have to have a whole night for Green's theorem, so this may actually include Green's theorem and the surface integral flux stuff. Okay, so but we should. What are we finished by this coming? This Thursday night of next week. That will end the material for test 4. Okay. All this material, the blank notes are posted online under test 4's cluster on D2L. So just to make sure everybody knows where to get this stuff. On our D2L page. Yeah, if you're on our D2L page and you click on test 4 notes, that's the actual notes that I scanned in from what we did this past, last week. I guess I couldn't, well, triple integrals technically starts test 4 material. So that's the lessons that we've done in class. The actual lecture notes, all the stuff that ended this last test was right there, polar triple integrals. So you want to make sure there's triple integral homework for this particular test 4. So I guess I probably should scoot that up while I'm thinking of it. So everything's kind of grouped together. So let me move the double integrals in polar. We'll just scoot this stuff down. So there's the supplement homework for triple integrals. There's the notes that we did in class. They're the blank notes though. And then the solutions to the triple integral homework right there. Okay, so what we've got is test 4 begins with triple integral, these notes, this homework, there's the answers to it. What we did this past Thursday, triple integrals and cylindrical and spherical, the supplemental homework on it, and I believe it has its solutions here somewhere.
I was going to ask you that. I couldn't find them.
No solutions? I'll find them. I've got it as a PDF in on my drive at some place. And this begins the notes that we're starting tonight. Vector fields, line integrals, and everything that would be on the typical last test. Now be careful right down here. If everything gets overloaded on one particular module, this little load more prompt shows up at the bottom. So if you need to click that, that actually takes you through the rest of the stuff. So the notes for vector fields and line integrals technically go all the way down to here. Well, no, down to here, and here, and here. Okay, so that's all that stuff. And then test 4's homework packet is all one document. So it's not individual documents. So that right there is your homework packet. And I've got the short solutions, kind of like the version of checking the back of the book. If you just want to check to see if your answer is correct, that's what the short solutions are. The long written up solutions are also available. So I'll probably post those there at some point too. Yes, sir?
What's the Jacobian for the triple integrals?
The Jacobian for our triple integrals, for spherical, it was rho squared sine phi. And for cylindrical, it was the same as polar, it's just an extra r. But are you asking a bigger question as to what the heck a Jacobian is?
No.
Okay. Yeah, so the only Jacobians we're going to need are the one for polar and double. We've already done that. And then the triple cylindrical and triple spherical. Yeah.
And pi can only go from 0 to pi?
0 to pi, yes. Any questions? Who didn't get their test back yet? Okay. Thank you, sir. Your map.
Yes.
Okay. And this also passed around, Matt, if you want to commit to retaking a test. Just choose one and hand me that document when you're done.
When are we supposed to retake them by?
The retakes will begin this Thursday, and they'll be in there until next Thursday. So whichever one you want to retake, I'll double check the list. I'll make a new version of each of the 3 tests, and then I'll have your name on the test. Thanks. So please stick to the test you commit to, okay? Because I'm actually going to type your name on the test copy that you go to take in the testing center. So if you decide, on the 29th of April, oh, I want to retake test 2 instead. Yeah, sorry, you need to give me a little more warning than that. So I make sure I have enough copies in there for whoever wants to retake it, okay? So if you change your mind, try to let me know soon. Anybody vacillating on which test they want to retake? Maybe.
I'm sure yet.
So try to commit, because I think I was trying to predict yours earlier. And I think I put a question mark by your side. I didn't know which one you want to choose. So just let me know as soon as you can. Ideally by Thursday of this week, because that's when I want to put.
I'll send you an email.
Okay. So yeah, if you're still kind of teetering as to which one you want to retake, just try to let me know by Thursday so I'll know which one to definitely have in here for you. All right. So there's the stuff that's remaining. All the supplemental homework is right here for the vector fields and the line integrals and the surface integrals and the flux and all this good business. And again, those are just the short answers, but I will put up the long answers. And I also need to find the answers to the cylindrical spherical, because they should be on there somewhere on my H drive. So, going back to the document camera, what we're starting tonight. And I'm actually going to need to pull up that software package that I do a little graphing with once in a while, because some of these vector fields are kind of hard to see, so I'll want to kind of see what some of these look like, what a typical vector field is. A vector field, you can have a vector field in 2 dimensions or in 3 dimensions. And the way it's defined is, if you have a vector field in 2D like this, you're going to have an I and a j component because it's an infinite set of vectors. A set of vectors that depend on which position you're at in the xy plane. See, I've got an example of a 2-dimensional vector field right here. It's a capital F, so the dependent variable is capital F, and notice it's bold font, which means usually whenever you're writing these down, you probably put a little arrow over that because it represents a vector, just like you usually do for I and for J and stuff like that. But keep in mind, in type text, that's usually just a bold letter that's going to let you know you're dealing with a vector quantity. So the vector field is a function of x and y. It's a function of every point in the plane. And you use the xy coordinate in this way to generate the vector that's tailed at that particular point. So I've picked some just random points here in the xy plane to show you what some of the vectors in this field would look like. So if we're right here at this point is x equals 3, y equals 0. And it produces a vector by taking 3 for x and 0 for y and plugging into this as a function. But notice your output's going to be a specific ij component vector. So the vector that's tailed right there at the point 3, 0 would have an I component of 2 times y, so the I component is 0. And the j component is negative x times j, which would be negative 3 times j. So you actually use the coordinate of the point where you're using as an input to generate the vector that the vector field makes. So the specific vector that's there would be the vector 0i, and then minus x, so minus 3j. So you have a vector that looks something like this, tailed at that point, going 3 clicks down in the j direction, looking roughly like that. Okay. Picking another random point. That one was on the x-axis. If we use this one that's on the y-axis right here, this is the point 0, 1. So if I take 0 for x and 1 for y, this is going to be the tail of the vector that this generates here. So whatever point you're plugging in is always going to be your tail. If I plug in 0 for x and 1 for y in the vector field's equation, the I component becomes 2 times 1, so you actually get a 2i. But then your j component is based on x, so it goes to 0j. So you actually get a vector there. The f vector is 2i. So tailed at that point, going 2 clicks in the I direction would be something roughly like this. So you kind of get the idea of how a vector field is generated. It takes any point in the plane, and just like a function, you plug the point's xy coordinates into the way that they're used in the creation of the vectors, and that tells you the vector that that particular point produces in the field. This one over here, this random one in the second quadrant, that's the point negative 4 for x, positive 2 for y. So if I take that and plug it in, my I component will be 2 times y, so I'd have a 4i. And then minus x times j will be minus negative 4, so plus 4j, bless you. And so that will be the specific vector in this field that's tailed at that point. So tailed right here, 4 clicks for I and 4 clicks for j, makes its head go up right there. So depending on which point you're using, you can produce, any kind of random looking vector, but they're all, I say it's random, I'm picking random points, but there is a pattern to the vectors in this field, all based on that definition in the vector field itself. Drawing vectors by hand in a vector field really, really sucks. Because, there's an infinite set of points, there's, if you actually start graphing every vector at every point, you get longer vectors and shorter vectors overlapping, and it kind of starts looking like this, like a big old mishmash of pickup sticks. If you don't know what that game is, I'm sorry, that's an old game. I'm an old guy, and I make old references. But just to show you a better representation of this vector field. I've got the new Calc program pulled up here, the one we've done some 3D graphing on in the past. And you can also do vector fields on this. The way you do it is you open up a 2-component vector. It looks like a 2x1 matrix. And then what you set this equal to is you set it equal to another 2x1 matrix. And the equation is set up this way. This is the I component for your vector field, and you set it equal to the formula right there. This is the J component for your vector field, and you use the J component's formula right there. So this is just saying I'm starting a vector field that has these components. The I component, I believe, was 2y, so I'm going to put a 2y right there. The J component was minus x. So it'll take the vectors, it'll make vectors into the two dimensions like this that are based on that movement. However, the scale is a little off kilter. See, the vector that we got right, let's see, which one did we use? We used the point 3, 0. Right here at this point, we got a vector that said negative 3j. Was going 3 clicks down in the j direction. But notice, I mean, first off, there's no vector actually drawn there. But even if you zoom in closer to it, to that point, right about there, pick up a vector and try to tail it right there as best you can. Oh, so close. There we go. Stop it. Good deal. I've got it exactly at the 3, 0 point. And it tells me that the x and the y components are 0 for I and negative 3 for j. But does that look like it's graphed to scale? No, it's not. I mean, if I see a vector there that's supposed to have a negative 3j component, I mean, there's positive 3 itself. It should be much, much longer than what that indicates. The direction is correct. What this software package is doing is it's shrinking the vectors down relatively so that you don't get this big mishmash of overlapping vectors that looks like a big set of, someone took a big set of straws and just threw them on the floor and just, randomly placed in the plane. So you can kind of see the movement of the vectors. See, this particular vector field looks like, well, just some kind of circular swirling whirlpool or something like that. All based on the actual formula that's used for the I and the j component, the 2y for the I and the negative x for j. If you switch them around, or make a subtle change, like what do you think is going to happen if I change this j component to positive x instead? It's going to keep the same numbers, the same, each vector will have the same magnitude, but the j components are going to go in the opposite direction. So most likely, it's going to give you, well, no, not another swirl. It actually gives you a whole different shape. Just changing that minus sign gives you this sort of hyperbola-looking set of vectors out there in the plane. Yes, sir?
Do they use the same type of software for mapping wind patterns?
Could be. I mean, every time, whenever you see, it looks just like we got a big, storm front coming in this way with, winds from the northeast. Yeah, that's exactly what a vector field represents. Whenever you see the meteorologist talking about, the wind coming in from a certain direction, he's using a vector field to represent the currents of the wind coming in that direction. Or even flow, different flow levels of a river. Usually you may have, faster flow toward the top, or in some cases faster flow toward the middle. So you can have small vectors representing the flow here and here, but then longer vectors representing the flow there that are closer to the center of the river or something like that. What's something else that this kind of reminds you of?
Slope field.
Slope field from differential equations. Yeah. And how you're going to say something?
I was going to say
slope field. Okay.
magnetic field.
I was going to say magnetic fields. Yeah. I mean, not necessarily seeing the repulsion there, but yeah, whenever you see those vectors that represents the different kind of forces the magnets are repelling or attracting from each other, you can see sort of images like this. So some of you have seen uses of vector fields just by recollection of watching the weather report or your physics class or differential equations class. So you've seen these before. Just be careful. Slope fields are a little bit different. The only difference is slope fields just tell you the direction of the tangent lines as you're trying to draw a solution to a differential equation. This has a specific orientation to it. So if you were to treat this as a slope field, remember the tip of each of these little Q-tip shapes represents the head of the vectors. So if you were to sort of draw a path through here, these vectors would indicate movement in that direction. If you started right here, the wind current or whatever this is would push you probably like right about there. Okay? So it's the easiest way to draw a vector field is to get some kind of software package like that, because whenever you're doing it by hand, I mean, look, this is nowhere near as pretty. It's just, I just picked some random vectors out there in the plane and just plotted them. And see, just to give you a heads up on the homework, some of the first problems that you see in the supplemental homework, I got a copy of it right here. I give you some examples of vector fields up here, and then I've given you graphs of what they're supposed to look like. But it's a one-to-one correspondence. Each of these vector fields corresponds to one of these 4 graphs. So what you might want to consider doing is, you know, if you're trying to match B here with one of these 4 vector fields, maybe do the same thing that I did right here. Take just a piece of graph paper, or even make your own little makeshift piece of graph paper, or even overlap it with some of the graphs on this, and see, well, if I use the point, you know, 3, 3, what would that vector produce, okay? And then try to look at that same position on here to see which of these vector fields produce something that's going in the same direction as what you get. Because the pictures I get this from, I'm getting these pictures from that same software package. So one thing you gotta be mindful of is the vectors you see here are not gonna be as long as the vectors that you get if you draw them freehand. They're gonna have the same direction that they should, but they're gonna be scaled down so that you don't have a lot of overlapping vectors in the vector field. Okay, and that's the only drawback of this software is, I mean, it's not a bad drawback because you can actually kind of, you know, at least see the motion of the vectors in the field. And notice, you do have shorter and longer vectors, like on this one, the closer you are to the origin, you still see a swirly pattern to it, but the vectors seem to be a lot smaller. And the further you get away from the origin in all directions, the vectors seem to get longer. So, I mean, it does give you a sense of the way the magnitude of the vectors in the field change, but it just tries its best not to make all the vectors overlap to where it looks like, you know, a big pickup sticks game or something like that. Okay. So the first few problems are just like this. I just want you to match a vector field with this graph, because that's typically seen in this section of almost any Calculus 3 textbook. Another vector field that you're kind of familiar with is the vector field that you can get from the gradient of a function. See, this was on your last test. If I come up with the gradient for this vector field, or for this function, remember it's the partial of f with respect to x is your I component, and the partial with respect to y is your j component. So if I actually create the gradient vector field here, and think of it as a vector field, z equals x squared minus y squared, so the partial with respect to x would give me a 2x for my I component, and the partial with respect to y would give me a negative 2y for my j component, okay? So if I wanted to sketch a vector field that comes from the gradient of a scalar function, there's a kind of a subtle hint there. Remember how the gradient of a scalar function produces a vector field that, well, remembering how the gradient produces a vector field will come in very handy here, so I don't actually give you the complete hint. But how did you draw gradients on test 3? There was one problem where you had to draw a couple of the gradients on some, well, in one problem. How did you do that drawing? It was, I think, problem number 2.
Pointed the gradients
First page.
toward the peak and made sure that their magnitudes coordinated with their level curve.
The steepness, yeah. The magnitude of the gradient represents the steepness, so on a steeper part of the curve, the gradients got longer. On a shallower part of the curve, the gradients got smaller. And they're always going to be perpendicular to the level curves, pointing uphill, or pointing, you know, in the increasing z direction. So the easiest way to create this kind of vector field is to go ahead and sketch some of the actual level curves of this. So let's say, if we're making level curves, let's pick some z values that will probably be kind of handy here. And again, this is probably a little bit of a graphing deficit because, well, it should turn into a curve that you might regularly recognize. If I choose z values, let's say z value of 1 and then 4 and then 9. So I want the level curves that correspond to those particular z values. Z equals 1, z equals 4, z equals 9. So if I take my original surface up here, I'm essentially setting x squared minus y squared equal to 1, 4, and 9 separately to produce each of those level curves. And the reason I'm using 1, 4, and 9 is that's kind of handy with this particular curve. Anybody remember what kind of curve that equation produces?
Is it a right side semicircle?
No, if you have a sum of 2 squares, it's going to always be a circle, or at least an ellipse. A difference of 2 squares, have any of you heard the word hyperbola mentioned at all this semester at any point in time?
Yeah.
Okay, so do you recognize the equation x squared minus y squared being a hyperbola that opens along the x-axis? No, didn't do that too much. Okay, so that's you know, that's where me and Beth differ. So for each of these level curves, so in this kind of problem, if I gave you the level curves, you could sketch the gradient vector field a lot more easily. So let me just do that.
I mean, for when you back out of it, it kind of just looks like a big X.
Yeah, it looks like several, almost like concentric x's. So you have a hyperbola here for z equals 1. So give me a second, and I'll go ahead and fill in some of these level curves, because each one of them is going to be a hyperbola. At z equals 4, so again, this was z equals 1 right here. Z equals 4 produces similar looking hyperbolas that kind of taper and get close together. The further they go apart, they kind of get closer at their asymptotes. And then for z equals 9, you get another set of hyperbolas that kind of open to the left and the right. They get sort of closer as the further you get away from the into the quadrants like this. Okay, so if I were to sketch some gradients, and again, let me pair the z values over here. This one was z equals 1, this one is z equals 4, and this last one was z equals 9. So with those level curves plotted, you can get an idea of which way uphill is. On this part of the surface, z equals 1, 4, and 9, you're increasing this way. And this actually turns into, this is a hyperbolic parabola, it's a saddle. So this is the part of the saddle that's going up like this. The level curves here will produce the part of the saddle that's going down below the xy plane, okay? So for just these few level curves, if you wanted to sketch members of this vector field, you can keep in mind that these gradient vectors are going to meet each of these level curves perpendicularly, and they're going to be pointing in the increasing z direction. So if I drew some of those in blue, like right here, you'd have a gradient vector that may look something like this. But then right here, probably a little bit longer. Because why?
Steeper than closer together.
A little bit steeper right there. So same idea down here. You know, have some kind of magnitude like this, and then a little bit of a longer magnitude there for your gradient vector. So based on these curves and the increasing z direction, the members of this vector field would probably look something like this when you kind of graph a good many of them together. So that way, if you know it comes from a gradient, then you can kind of create a lot more vectors than you can just by plotting points like we did in the first example. Same idea over here. The increasing z direction is going this way. So all these gradient vectors will be looking something like this. Perpendicular as close as you can eyeball it to the level curves, and then pointing in the increasing z direction. Okay, so roughly kind of like that. Those are not the only level curves. If we go in the negative direction, it produces some more hyperbolas that open along the y-axis, and you actually get some more that are kind of doing like this. But just for those few level curves, if you had just a few graphs like that, it can help you get a good representation of what the overall vector field looks like. Let me show you what it should look like. The I component was 2x, the j component was negative 2y. So for just the few level curves we've got, and let me go ahead and actually do that. There was one of our level curves, I'll graph it in red. The second one was x squared minus y squared equals 4. So just that pair of them. Graph them both in red.
You have to
Zoom out a little bit so we can actually see them together. So you can kind of see, you know, if those are the level curves of the surface, and they are, the gradient vectors kind of meet each of those level curves at right angles. And you do have smaller vectors here because these level curves are further apart. But the more you zoom out of this graph, the hyperbolas that represent these level curves get closer and closer together. On the upper left, upper right, lower left, and lower right, they get closer together. So you get longer gradients there because that's technically a steeper part of the surface. So that's one of the easier types of vector fields to generate, is a vector field using the level curves for a function and overlapping gradients with those level curves. Because you just need to go perpendicular to the level curve. And remember, longer gradients when you're further, when you're steeper, when the level curves are closer together. Shallower gradients when they're a little further apart. Okay. But of course, the more level curves you have here, the more gradient graphs, the gradient vectors you can actually draw. Okay. So, the other homework problem that this kind of pairs with is, down here at the bottom of this first page. I didn't actually give you any kind of a grid of graph paper, but I let you know that I want you to determine the gradients for these particular functions, and then after sketching some level curves, you know, these shouldn't be too hard to sketch level curves for. Your level curves here, if you use z values of 0, 1, 2, 3, each level curve should be what kind of shape? Based on y minus x, or x squared minus y. Parabolas, yeah. If you use, for example, the f value, the z value 1, You'd solve that as y equals x squared minus 1. If you want to solve it as a function, you can graph it in your calculator. So the level curves here should produce parabolas. Each one should be opening up. This one, what would the level curves here produce?
Circle.
Yeah, if you set this equal to, and keep in mind, your range here would be only positive numbers, so you should only set this equal to like 1, 2, 3, 4, 5 values for z. And each cross-section or level curve will produce another concentric circle. So your gradient vector field here will be based on concentric circles opening outward. So all your vectors in the gradient should almost be going outward like that, because going uphill would be looking like this, with all the level curves when you overlap them together. Okay. All right. But the gradient, the gradient vector fields, the plotting the vector fields, that's kind of, I don't want to say it's incidental. I'm just introducing you to what vector fields are, because the main thing we're going to be doing with vector fields is calculus with them. We're going to be doing some integration inside these vector fields, and I don't think it's too premature for me to go and give you a heads up on it. The other main focus for tonight is to introduce you to line intervals. First and foremost, every integral you have ever done, beginning with calculus 2, is technically a line interval. You've integrated over a line segment of the x-axis from x equals a to x equals b, and calculating something like area, volume of a revolution solid, a work calculation, lifting an object up a well or something like that, and different kind of integral calculations. Any integral you have done is technically a line integral. And the word line here is a little bit of a misnomer, because there's three different types. There's the ds type of line integral. The way I characterize these line integrals is by the different kind of differentials you see with them. The differential that's actually used on the end of the line integral like this. Some of the differentials are ds. There's a ds type of line integral. The ds stands for arc length. You're actually integrating a function with respect to some kind of curve in the xy plane. And so instead of you integrating over the straight x-axis, you may be integrating over part of a semicircle or part of a parabola. You're using that as the domain of your integral, which is kind of hard to see at first, but I can show you a picture of what that stands for, all right? There's also differentials of dx, dy, dz. These are not triple integrals. These are just single integrals that have, separate differentials for three different parts of what you're trying to integrate. And actually, I really need to switch the position of these two. I should show you the f dot dr type of line integral before I show you the dx, dy, dz type, because these dot product integrals are the ones that we actually are going to be using vector fields with. So let me jump ahead to show you what that's all about. 3 pages in the future to where you're talking about the f dot dr type. This is actually going to calculate work. You have the vectors in a vector field like this, and you have some kind of curve that you're trying to push a particle along. You want to see what kind of work are the vectors, maybe the force vectors in this field doing in pushing a particle from this point to that point on this sideways half parabola path, okay? And to calculate work, well, how do you calculate work in physics?
Area under.
Well, more rudimentary than that.
Integral of force with respect to distance.
Okay, so or just, if you have a variable force, yes. If you have a constant force, it's just force times displacement. That's it. But if the force does vary, and since these vectors do represent your force vectors, different vectors have smaller magnitudes, some have longer magnitudes, you do have a varying force that represents the work in pushing a particle along this path. And it's not a straight path either. You have to consider the curvature and the way the path kind of arcs along like that. So in calculating the work here, you do have to do an integral because the force varies and the path isn't straight. Because the easiest calculation for work is I'm pushing with 10 pounds, I'm displacing 20 feet, I'm doing 200 foot-pounds of work. If the force is constant and the displacement, is in the direction of the push, okay? But if your force varies, you're pushing harder than slower, and then even have to turn around a corner, it requires a little bit of integration, and you have to know some kind of function that tells you the pulse of the force, how it's stronger pounds here than weaker pounds in other parts, stronger than weaker. Maybe some kind of sine function or something models that particular oscillating force or something. But if the force varies, you do have to integrate. So what I want to do is in your notes, I want to go over the ds type first. So keep this page as it is, but take this page that begins with number 2 and switch it with this page that begins with number 3, because I want to actually kind of get you into those in that particular order. Okay. So the first type of line integral the DS type. And let me go on and show you what the problem's all about. You're asked to evaluate the line interval, and this is the format for what a line interval looks like. You're using a function with two variables because it's still over a two-dimensional domain, but you're integrating over a curve C. The curve C has to be given to you somewhere in the problem, either as a parametric equation for maybe a semicircle, or at least referred to here. The curve C that you're integrating over in this case is the straight line segment that joins these 2 points, going from the 1, 0 point on the x-axis to the 0, 1 point on the y-axis. Okay, now what this is measuring, you're integrating the function x squared plus y squared, which there's an actual picture of it down here at the bottom of the page. This is the surface, and the graying out is kind of frustrating, so you can actually see what's going on here. Let me put some tracing lines in here. This is the function that you're integrating, that paraboloid. Now, if you're only considering, the base being an area, you need a double integral. I'm not integrating over a two-dimensional area like we did previously, where you're integrating over rectangles or integrating over regions bounded by functions. I want to integrate on this line segment that goes from the point 1, 0 in this direction to the point 0, 1, from the x-axis to the y-axis. So keep in mind, that's just a line segment that's my domain. I want to integrate this function with respect to that line segment. So technically, this is measuring the same thing a calculus 2 integral does. What you do is, in the process of building this line integral, is the curve that you're integrating over is projected upward to the function that you're integrating. In other words, the paraboloid here. So every point on that line is projected upward, linked with a z-value, and you're technically measuring a two-dimensional area. Okay? You're actually measuring, just like in calculus 2, whenever you integrated the line segment from A to B, and then you had a function that defines the top of your curve, you were finding the area between the x-axis and the graph that was on the top. Okay, that was one of the first applications of integration you ever saw in chapter 5 of your textbook. This is the same idea, and this is really no different. It's just funky as to how you set it up. You have to set it up based on this being your arc length, this being your x-axis down here, this straight line. But this doesn't have to be a straight line. This could be a semicircle or a quarter circle that links these 2 points, and then that would give you sort of a curved shape that connects up to the paraboloid, and it would still measure this little two-dimensional slice that's going from the xy plane up to the surface. It measures the area of that piece. So based on the geometry, this should be a positive measure. It should be some positive number because the function is up above the xy plane, and we're integrating over that particular line segment. Here's the setup. Here's the way it sets up. At the top of the page, it says, to evaluate a line integral of the DS type, you're going to need to have a curve C in parametric form. So there's some work implied here. I need to parameterize the curve C and come up with parametric equations that represent this line segment that begins at the point 1, 0 and ends at the point 0, 1. How do you come up with parametric equations of lines? There's 2 things you need. Okay, with any line, you do need a slope and a point. But thinking in terms of vectors, the parametric equations of lines you dealt with earlier this semester, what were the 2 things you needed to find a 3-dimensional parametric line set?
Unit vector?
Or just any vector. It didn't have to be a unit vector. You need a vector that describes the direction going from one point to the next on the line. And that's like the 3-dimensional version of slope. And you need 1 point. You need a point. So if I use this as the beginning point, I'm going to use the point 1, 0 as my beginning point. Do you remember what value, what role the point plays in building your parametric equations?
T?
They're not the t coefficients. There's one part of the contribution becomes your constant terms. The other part of the contribution becomes your t coefficients. The point that you're starting with is your constant terms. So use the point as the constant.